welcome again to everybody. I'm Cristiano, lead AI scientist here at PySchool, and this is our, let's say, first tech talk for session 13 of the School of AI. We will have many others from, let's say, this week till the end of September. Obviously, with a small break during August. And so welcome again, and today it's a pleasure to host Simone Scardapane. Simone is a tenure-track assistant professor at Sapienza University in Rome. His research is focused on many things, in particular graph neural networks, explainability, continual learning, and more recently, modular and efficient deep neural networks. That, by the way, will be I think the topic of today tech talk. He has many publications, and he is also let's say an old friend of PySchool from the very beginning. So again, today Simone will talk about designing efficient and modular neural networks. Welcome again, Simone. I will leave you the floor.
Thanks, Cristiano. Very nice introduction. I'm happy about this tech talk. I hope you can hear me correctly. Maybe, Cristiano, can you confirm this?
I can give you 5/5. So
okay.
Perfect. Yes.
So can you see the presentation?
We can see it.
Okay. So the first, I like a couple of 2 or 3 disclaimers, let's say, before we start. So first of all, this is a presentation I started this year because, as Cristiano was saying, this is a topic that has gained a lot of interest for me over the last year, and I wanted to put together my thoughts on these ideas of modularity, efficiency, etc. And this presentation is what came out of it. And I presented it at summer school recently, and I'll present it again in a couple of months after the holidays. So I hope you enjoy it because it's a bit, it's sort of a high-level overview of what I think will become very important in terms of modularity and neural networks. What I'd like to, but it's a lot of ideas, let's say, thrown around, and I hope at least some of them can stick. The presentation is by me, but I will sometimes show some things we're doing on these topics, which could be interesting also for collaborating or for other things. And in this case, I'd like to thank all my collaborators. Some are from Sapienza, some are from outside Europe or US, some are PhDs, etc. And if you want to learn more about this, my website is more or less complete. I try to keep it up to date, and I'm also very active on Twitter, although now it's not really, it's a drawback, it's not an advantage. So what I'd like to talk today, again, it's a bit high level, but I like to think of, I like to categorize typically neural networks in terms of what they can handle, let's say. So most of what for example, I teach at the university, and most of what we know about neural networks, most of what we teach is, okay, those are neural networks that are very good for images. Those are very neural networks that are very good for graphs.
Simone, sorry to interrupt you. We can hear you very well, but the screen somehow, okay, now it's loading. Okay. Because we were not able to see the presentation.
Maybe let me share the entire screen so I don't have any issues of this kind. Can you see the slide now?
Yes. Now
is it updating now?
Maybe you can go back at the very beginning. Yes. Now it's also updating.
Okay. So that was the title. That's the whole lot of people that are. I'll give you the link at the end of the presentation so you can check every person in turn. And oops, I went the other way. But anyway, there is something very interesting for neural networks, which is that what I'm calling here the architectural bias. It means that if you have a certain amount of data and you have a certain number of budget, let's say computational budget, so a certain number of parameters that you can handle, the way you organize your neural network, the way you organize your parameter can change drastically everything in the way you but it can change the time it takes to get an answer. It can change the easiness of optimizing this thing. But what I like to show you in this talk is that it can also change dramatically the properties of this neural network and what you can do with these neural networks in terms of explainability, efficiency, multitasking, and so on. And there are some properties, let's say, that are so used today and so known, let's say, that we don't even think about them. But for example, even the idea of, let's say, taking this budget and splitting it into a number of sequential layers. So sequentiality is a property. It's a decision we make in how we build this neural network, and it gives us some interesting properties, for example, in terms of separability of certain functions. Recently, every neural networks we see can be cast, for example, in terms of what I call here residuality, but it means that your neural network, it's not just processing a certain datum, but it's actually adding corrections to this data. And this is interesting because, yeah, it works better. So it typically residual connection improve your performance, but they turn your, I don't know if you know this, but they turn your neural network into a approximation of basically a stochastic differential equation. So you can connect now your neural network to a whole field, let's say, of numerical optimization, and you can, for example, apply different solvers in continuous time to train and optimize these things. So you make a small change in the way the neural network is made, and you drastically change what you can do and the way you can interpret this neural network. And there are many more. So convolutional neural networks have locality, you have weight sharing, causality, for example, in these large language models and so on. And what I wanted to talk about is what I'm calling here modular sparsity. And modular sparsity is the idea that in the future, what we will do probably is designing these neural networks so that only parts of the network will at any given time. And the network itself will probably choose what component to instantiate at every time. And if you think about it, it's a little bit more close to the way we use computers. So we have a lot of stuff in a computer, and we almost never use the full power of a computer, except, for example, when we are processing a video or playing a very high-intensive video game. Most of the time, the computer is idle, and maybe we open a Word file and use a little bit of CPU and a little bit of memory. And in particular, if you think of a very simple neural network, here I have green dots, green circles, because most of my presentation will be targeted to transformers, but actually some of the ideas are more general. In principle, that's the standard neural network. So you have an image, it goes through the neural network, and everything is active. But in principle, you could do something different. For example, the network could decide to focus only on small parts of the input. For example, if you have a horse, you can decide, okay, a lot of the background is completely worthless. I will throw it away. And so I will, let's say, have a certain improvement in computational efficiency. But maybe some layers also are useless. So there may be some layers that are not really doing anything for this. So I may be able to skip them. And even inside each layer, if you think of the layers as feature extractors, maybe not all of the features are particularly interesting. So I may be able to activate a small number of blocks. So you see, we do the same thing, but we program our network, we design our network so that only small pieces are active at every time. And what I'd like to do in this talk is to say, okay, first of all, we need to understand how we can do that. Okay, can we design neural networks in this way? And of course, the answer is yes, and I will show you some trends that are doing this in the literature. But the second thing is more interesting is once we start doing this, okay, so if our neural networks become modular in this sense, what kind of interesting things can we do in terms of, I don't know, interpretability or efficiency that we couldn't do before? And there are many of these. I'd like to give you just an overview. But first of all, these things are interesting because they give us, for example, what computational costs from the number of parameters. Because if we only activate small parts of the neural networks, we are able to have a huge amount of parameters, but at any given time, only a small number are active. And there are some rumors that this is the way, for example, GPT-4 is working. But what is more interesting for me is that this cost can vary. So now we have neural networks that are going everywhere. I come from a telecommunication department. I will show you some examples, but now we are in this 5G, we are going towards 6G telecommunication paradigm where neural networks will be everywhere, will do everything. Let's say we'll compress information, throw it over in a network, decompress it on another place, we'll estimate the channels, etc. And in this context, everything can change. So maybe I have a neural network on my cell phone, but I don't have a lot of battery. Or maybe I need to send data over a network, but I don't want to send too much data. So there are situations where my resources are low, and there are some situations where they're high, and I want my neural network to react in an elastic way. And there is what I call here encapsulation. So ideally, I should be able, if I put everything into nice blocks, to make it more interpretable, and we'll see some of these. And as we will show you, these are also very nice and very interesting for multimodal and multitask problems. So they give us a nice way of encapsulating things of different tasks, for example, in different parts of the neural network. What are the issues? The issues is that if we go back, sorry, to this figure, so basically what I need is a layer that I can train that allows me to do this sparsification. So I need some automatic way of training the network so it can take, for example, a patch here and say, okay, I will keep it or I will discard it. I will skip this layer, or I will keep this block, or I will activate this block. So all these are discrete decisions that the network needs to make to work in this fashion. So again, I want this not to be a fixed pattern, okay? This is a pattern that is trainable and that the network is choosing depending on the specific, for example, input. So for example, the background will change from image to image. So I need to adaptively select which part I'd like to discard. And so this is a discrete problem. So I need a way to plug in something to plug in, it's able to discretely remove some parts. And typically that's supposed to be a very hard problem because it's hard to fit discreteness with backpropagation, basically. But I will show you that today we have some very good ways of doing this. And typically that's done through reinforcement learning. I'd like to avoid reinforcement learning because I don't really like it. And I think it's an overkill for, let's say, 95% of the problems it's applied on. And if you're interested in this is a very general topic, okay? I don't want to, presentation. I don't want to go in depth into a lot of topics. I don't want to give you all the math, etc. That's a sort of high-level overview of the main concepts. If you're interested, there's a survey that came out, not my survey, a few months ago, pushing this idea of modular deep learning. And it's a bit more general than what I discussed. It covers more use cases. What I will cover is mostly this very bad-looking picture here. This is the third one, function composition. So activating certain parts, certain functions of the model. Oh, by the way, if you have questions or anything, I think you can interrupt me at any time. I'm happy to answer anything. So there are 5 parts, the quick parts to the presentation. So the first one is, how do we do this? Okay, so to do all these things, we basically need at least one way to select these components. So if we have this object, let's say, we can do all of these things. Okay, so the first part of the presentation will be introducing this object. And the second part will be taking this object and trying to apply it to many different use cases and see what has been done in the literature and what we get by applying this trick. And I will show you the simplest possible way of doing this, which is called the Gumbel-Softmax tricks. It's pretty common today in a lot of literature, actually. I will give you some pointers at the end because this is just, let's say, the simplest way of doing something in a discrete way inside the neural network, but there are many extensions and ideas, etc., that can also be applied. So what we need is a layer, basically, that we can take, we can plug in the middle of the neural network. That can select surface. Can select here, and it can select whether to which blocks in a layer to activate. So the main component, let's say, in this is, and typically we'd like this component to be, this reason, I think it's understandable. We don't want it to be deterministic, but we prefer it to be probabilistic because we'd like to explore a little bit. So we like the neural network to explore different things with different probabilities with some pre-specified, let's say, level. So what we like is basically a way of sampling from a categorical distribution. So the idea is that we have a certain number of things we want to select. So for example, this could be all the patches of my image. And my neural network will, so there's okay, this is a little bit more mathematical, but you can skip it. But basically, each of these patch is represented by a one-hot vector, which has a 1 in the corresponding index. And my neural network will predict some parameters, and we will have one parameter for each patch, for example. And what I'd like to have is basically this scenario. So I have my patches here, my neural network. My neural network is predicting some scores. And here in the middle, I want to take a discrete decision based on these scores. And then I will use this discrete decision to, for example, remove some of these patches or keep some of these patches. And let's take the simplest, possible decision. The simplest, what the simplest possible decision is that I have a score for every choice here, and I want to take the maximum. I can interpret this as basically unnormalized probabilities. So you see 1.3, 0.2, 0.7. So this is telling me that the first choice here is probably the most important one. So what I'd like to do maybe is just maximize this probability and take the one-hot vector corresponding to the first element. So this could be a one-hot vector telling me that among these 3 elements, I should take the first one. And then there's some other neural network part that will use this object to do stuff, let's say. And so if we only have 2 choices here, we have a binary choice. So for example, this could be keep a patch or remove a patch, or maybe this could be different layers. And so I'm choosing which layer to execute. And we'll see other examples in the following. But first, we need to, let's say, solve the issue here. And the issue here is that this maximization here, so selecting the highest value here, is very hard to optimize because its gradient, it's almost always 0. It's non-zero only when you have a discontinuous jump from one maximum to the other. So it's really hard to optimize because basically we will almost never have a gradient and the backpropagation will break. By the way, this part is a little bit more mathematical. If you want, you can ignore it until I get to the examples later on. I didn't know I'll go a little bit quicker here. If you care about the theory, you can go in the slides in the paper I mentioned. But basically, this is a non-differentiable thing, let's say. So the idea is to take it and turn it into a differentiable thing by relaxation. And in particular, there are some, let's say, generic relaxation that you can apply here. The first one is that the problem for which it's not differentiable is that you're doing this over a discrete set, the discrete set of one-hot vectors, and which kind of corresponds here to the vertices, basically, of a triangle made like this. And you can turn it into a convex, nicer problem by taking the convex hull here. So basically taking all the possible points inside this object. And this makes the problem easier to optimize, but it introduces a lot of spurious, strange solutions, because now you can move freely inside this polyhedron, this triangle, basically. So typically what you can do, you can add some regularization to try to select a solution which is, let's say, as close as possible to one of the original solutions. And typically you can select an entropic for regularization. So entropy is a property of a probability distribution, and can vary, let's say, but the probability distribution with a very low entropy corresponds to a probability distribution where you're basically putting everything on just one element, and that's what we'd like. So it corresponds to taking basically a discrete one-hot vector, while with a highest entropy, we get a uniform distribution. But I mean, math apart, what is interesting is that this is seems like a very, very complicated problem. So it's a maximization inside this convex set, plus this regularization term, which is weighted by a constant. But it turns out that it has a closed form solution, and the closed form solution is just the softmax with temperature. So it's just, everybody knows the softmax. It's typically used in both in the attention layers in the transformer, in the output of a classification problem, but it takes our vector of scores and it transforms it into a vector that has values larger than 0 and that sum to 1. And we have this temperature now in the denominator. Basically, now everybody knows about the temperature because of GPT, but with a very low temperature, you will be, as you see here, so you have these cores here, and depending on the temperature, you go from the softmax will transform them into completely flat vectors to vectors that are almost exactly one-hot. So that's what we want, let's say. And so we have this parameter, and typically we can vary it a little bit during training. So the gradient, it's easier with high temperature, but the relaxation is better with low temperature. And we get this kind of thing. So we have our neural network, it gives us some scores, and we can pass it through a softmax, and we get us kind of like one-hot vector. But you see that we have not really solved we almost solved the problem, let's say, because this vector is not really discrete now, but it's very similar to the vector we wanted to obtain. And the final idea, let's say, is to combine everything and say, okay, what I'd like to have is a binary vector during my forward pass, because I need it for actually removing some parts. So I need it to be binary. So I can keep the argmax during my standard run of the neural network. But whenever I need the gradient, I can take a straight, basically an estimation. So I take a different route. And instead of trying to differentiate through the argmax, I remove the argmax and I put some approximations such as the softmax. So when you do the forward pass, you take the argmax, and when you go backward, you take the softmax. So you have binary values when you're going forward, and you have a nice gradient when you're going backward. And we can actually, this is not a full Gumbel-Softmax, we can actually generalize it, because this is to take the highest value. So here in this context, it will always give me this vector actually. But typically when we are training, we'd like to have some exploration, let's say. So maybe here, for example, most of the time we like to the first option, but sometimes we would like the third option because we'd like to explore what happens. And if the solution is good, I will get a very high gradient and it will improve a lot this specific value, let's say. So we like something like this. So instead of the argmax, I like to sample in proportion to these scores. So now I need the gradients, not just of an argmax, but I need the gradient of a sampling operation, which looks to be even worse, actually. But it turns out that it's just a very small variation of what I showed you before, and this is called the Gumbel-Max. So maybe some of you are familiar with variational autoencoders. variational autoencoders have a very similar trick in their middle block, which is called a reparameterization trick, which allows you to turn sampling from a Gaussian of any mean and variance to sampling from a Gaussian with a fixed mean and variance, basically. And here you're doing something similar. So instead of sampling directly from this distribution, what you're doing is something strange. You are noising this distribution. So you are adding some noise here, and this noise is fixed. So in the sense that it doesn't have any trainable parameters. And it has a very special structure. It's sampled not from a Gaussian, but from a distribution that is called a Gumbel distribution, which is a doubly exponential distribution that has some special characteristic. You can completely ignore this. But let's say that we take this course and we add some noise, just some noise. And this noise is fixed. So when you compute the gradient doesn't go in this direction. So you see, we have nothing stochastic here on the path of the gradient, which is nice. And then we take the argmax. So you see the argmax most of the time will be like this. But if the noise there is sufficient noise here, for example, the third value will become the strongest one. And in that case, we will sample the third one. And it's really fascinating. But basically, if you do this, you can demonstrate that you are actually sampling from the categorical distribution. So this and this are the same, but this is much nicer because on the path and on this path, you have nothing stochastic. Everything that is stochastic, let's say, has been put as an additional input, which is basically constant from the point of view of backpropagation. Now we have again an argmax, but now we know how to, let's say, what to do with the argmax. So we combine everything and we get the full Gumbel-Softmax, which, to summarize, is a way of taking a neural network. The neural network gives us some scores, and we can sample binary values based on this score. Okay, so here the neural network will give us these 3 scores. To sample, we had this noise, this Gumbel noise. Then we take the argmax, and this will be a sample in proportion to these real values here. And I can use this in my downstream model, so I can keep going on. And when I'm computing the gradient, so I'm doing backpropagation, this thing is constant, so I can ignore it. And I take a relaxation here, and I use, for example, a softmax instead of the argmax. It looks very complicated, but it's already actually implemented in PyTorch. You can just call Gumbel-Softmax, given the scores, and it will compute both the argmax, the Gumbel, and also the gradient estimation, actually. So it will do everything for you. You don't need to implement this thing. Let me skip it. Again, just to tell you that this is just an introduction. Okay, just one way of sampling one element in a discrete way from with a neural network. There are many, many more regularizations, for example. There are other types of estimations. If you know reinforcement learning, maybe you have heard of reinforce, which is a completely different way of doing this. You can sample other things which are not categorical, etc., etc. There is an incredibly well-made survey here if you're interested into the topic. I won't go into the details here. Just to tell you here, I don't have the time to go. This was 1 hour and a half, actually. But there's a method in PyTorch if you want. It's functional Gumbel-Softmax. You pass the scores. It gives you discrete values that you can use to do whatever you want. And okay, now let's say we have a tool. Let's say a very nice tool, actually. Since I learned of it, I studied it a lot, and it looks incredible because it allows you to say, okay, I can discretize everything I want. I can take a discrete number of elements, of blocks, of layers. It looks like I can do a lot of different things. So I want to start, actually, I want to give you some examples of what we can do here in terms of modularity, but I also want to tell you what we can't do. So it's not how do you say, a golden, a perfect tool, let's say. There are some things that are not perfect, let's say. And in particular, just to give you an example, if we look at attention, this is just a high-level description of a transformer. So in a transformer, you get some inputs. They are converted into tokens. For example, you take patches, some positional embeddings are added, and you have the transformer. And inside the transformer, the most complicated part is computing the attention, and in particular, computing the attention scores. So you at some point, you will have some queries, some keys. So those are computed from your tokens, and you need to build this quadratic matrix that tells you how the tokens are interacting between themselves. And this is very problematic because it has a square memory, square time, actually, complexity. Memory only if it's implemented in a stupid way. It's an issue because, for example, right now, it's the biggest issue to scaling large language model to very, very large contexts. Because if you need to take a quadratic number of comparisons, it will soon become, let's say, unfeasible, okay? And that's what we'd like to, now there's a lot of literature on overcoming transformers to get back to models that have a linear dependency on the number of tokens. But if you have, let's say, this sparsification tool, you say, okay, but actually, who cares if it's quadratic? What happens if I can apply these ideas of sparsifying, discretely sparsifying everything, and I get lots of, I throw away, for example, a lot of here, I have this quadratic matrix, I throw away a lot of values, I put them to 0. So in practice, I have a number of elements that is very, very much lower than n squared. So even if in theory it's n squared, in practice it's feasible. And there's a lot of people that try to do something like this. For example, this is a paper from 2019, where they replaced the softmax in the attention with basically a very simple variation of what we did show before. It's not Gumbel-Softmax, but it's called an entmax. It's really similar. What is interesting is that this is a one-line code change. Okay, so you can take any attention implementation, you remove the softmax, you add this entmax as a plugin change, and you get a sparse matrix automatically, a dynamic sparse matrix. So it will give you sparsity depending on the tokens. It looks very nice. And then, so you ask, why is it not used more, let's say? And the issue is that, let me skip this one. It's actually really hard to gain efficiency from this kind of unstructured sparsity. So most of our hardware, it's actually not done, not optimized to work with zeros that are placed more or less randomly into a matrix. If you look this left figure, this black line is the let's say running time of some operation on the GPU with a standard matrix, let's say, and this green line is an NVIDIA CUDA kernel for sparse matrices, so matrices with a lot of zeros. And you see that the runtime gets better only when the sparsity is above 98%. And we typically don't get this level of sparsity by our methods, let's say. And now we have some better kernels, but they're also optimized with structured sparsity. So you need your values to be 0 in groups, specific groups, so that can be optimized in certain fashions. And that's really, really, really hard to make it work. So actually, and there are other ideas that try to do this. There is the reformer, for example. More recently, there is a group from Geneva that made something similar to work, but basically they need to reconstruct the adjacency matrix, sorry, the attention matrix in this block fashion, and they had to rewrite the CUDA kernel, which is really hard to do actually. A little bit easier than before, but still a bit hard. So what I like to say is that it's really good to be able to sparsify things automatically in a dynamic way. But if we want to use it for efficiency, for example, it's not enough to just throw some things to 0 and throw it away and hoping that it will get faster on our hardware, because our hardware is not really good with this kind of setup. So we need, if we want to make it work nicely, we need some other ideas, let's say. And that's the rest of the talk. So I'd like to show you 3 completely different design options for neural networks. So it's not just a matter of taking what we have and changing a little bit. At the Softmax, for example, we need to rethink a little bit the way we design these neural networks. But if we do that, we get some very interesting new paradigm shift. So we get completely, we can do things that we couldn't do before. We will see what I call here early exits. We will see a mixture of experts quickly, and we will see input, let's say, input selection. I don't know how to call it. So the first one is early exit. This is really interesting because it's a design change that it's not so hard, and it gives you a lot of improvements. So the idea is that if you have a neural network, basically, maybe you have a certain number of layers, but maybe you don't need all of these layers to solve a certain problem. So for example, this is a horse, horse, maybe it's a very easy horse to recognize. So if you imagine that you have exits, early exits, which are these classifiers that are attached in the middle of your neural network. If some of you is old enough to remember Inception from Google, Inception had a similar way of training in some variants. And you see, the first one is very early, and the prediction is actually wrong, because, I mean, maybe you need a little bit of time to get the good answer. But the middle one, it's the correct answer, and it has a good confidence, let's say. So maybe for our purposes, this second layer is enough. We take this exit, and we don't need to execute this part. So we could save, ideally, a lot of computation with just a snap of the fingers. And in order to do that, we need to understand a little bit how do we train these models, and we need a way of deciding, when we take this exit decision, and can we do something more in terms of efficiency. And the basic way, I will show you first of all the way it's done today. Google is doing a lot of work also on this. The basic way you do that is that for training, you just consider these classifiers to be independent. So you have one loss for each classifier, you sum all of these losses, you don't consider early exits. So those are 3 completely different classifiers. They are each trained to maximize their predictions. And then during inference, you do an early exit based on some, let's say, user-defined criteria. So for example, you can put a threshold over the confidence. You say, okay, I exit anytime the confidence is higher than 75%. So this is a non-differentiable threshold, basically. It's a non-differentiable criterion, but it's already pretty good. So for example, maybe some of you have heard of this confidence adaptive language model from last year. It's from Google. And basically, they took this idea and just apply it to a language model. And the idea is that in a language model, you are autoregressively generating tokens. And maybe some tokens are really, really easy to generate. So you see here below, the second token is really easy to generate. So it only needs a couple of layers. Some tokens are harder. They need more layers. And for example, the N is really easy and only needs one layer. And they basically apply the same structure we saw before. So they have a few early exit, basically here. You see this is attached to layer 7. And they have a user-defined threshold that guides when you exit. And this is, I think, 15 lines of code. And if you do that, they got some improvement of 30, 40 even percent line generation speed without sacrificing quality, basically. But I don't. What I don't like here is that basically you are setting these thresholds and you are doing this in a user-generated manual way. I don't like manual things. Let's say I think that it's a neural network that should decide all of these things. So what you could do, a more interesting thing, is applying what we saw at the beginning of the talk and saying, okay, but I do have a way for the network to automatically select which exit is the best one. So I know how to sample the one value, let's say, out of all k possible values. And here, k are my exits. So I have 3 exits, and I can add here, you see, I have an arrow that goes here. I have a block that tells here, okay, which exit is the good one for this input. So if this tells me 2, I will activate this classifier here, and I will exit here. So here the decision is trained, so it's part of the neural network. So it's done at training time, and it's the same at training and inference. So it's more elegant, and everything is done by the neural network. It's nicer, but also, let's say that here, you see here in this setup, each classifier is trained independently. We can't really tell the neural network that ideally we would prefer some herd. For example, if this classifier is already good, the network should prefer it, basically. And we have no way of telling it. But here we can do that because this is part of the neural network, so we can actually regularize it a little bit. And in particular, maybe it's a little bit hard to read this part. I still need to improve it a little bit. But imagine that I have this Zn is the, let's say, exit that has been selected by the neural network for a certain input, and the input is n. And for each exit, I know how much it costs. Okay, this gamma I are some estimation of the costs of each exit. And this cost could be a flop, it could be a battery consumption, it could be bandwidth, it could be a lot of things, let's say. And interestingly, we can basically build a regularization term, so something that we can add to the optimization that will force the neural network to take decisions that are optimal in terms of cost. So by let's say, if the loss is identical, it will prefer something with lower cost. And this cost could be, again, very varied. So it could be, let's say, typically how many operations I need to do to go to the next exit. So if this number of operation improves my loss, it's okay. But if it doesn't improve my loss, I will always prefer the earlier one. And I think it's interesting because it allows you to train this time, but optimizing for any, let's say, cost idea that you have just by gradient descent. You don't need to put additional threshold, optimization, etc. The network itself, the gradient descent procedure is optimizing for some optimal trade-off. And if you're interested now, we are trying to explore this into this telecommunication, 6G telecommunication field. This is a preliminary figure from a proposal we had this year. But basically, the idea is that if we get, for example, I can tell it, okay, do this prediction, but don't take more than 100 milliseconds, and don't spend more than 10 kilobytes of bandwidth. And I can do that by let's say, extending all these ideas. Okay, so this was the first major block. So you can, let's say, use this idea to select different decision points in the neural network. And by doing that, you can already do something interesting, which is regularizing, so optimizing for basically speed in a certain sense. Now I wanted to show you something a little bit different. So this is a mixture of experts. So in this case, instead of selecting one classifier, one layer, we split each layer into blocks. And we use our sampling procedure here to partition my tokens across these blocks. And this is called a mixture of experts. So the idea is that each of these mini blocks, let's say mini layers, is specialized in doing something, let's say. And this green block, it's called the router here. Basically, it routes the tokens to the block here, the expert, that is specialized in this processing. So maybe one block will specialize on the head, one on the tail, etc., etc. And this is interesting because basically here, even here I'm showing it with 3 experts, but even if we have a lot of experts, we will only activate those that receive at least 1 token. So again, we see this decoupling of parameter and computational power. So basically, we can have as many experts as we want, but we will only activate those that we need in a certain moment. And typically, you can use them in a lot of different ways. The common way you apply this is in transformers by taking the MLP blocks and turning them into this mixer of experts. So you see here, you have a standard transformer with a feed-forward network. You do the same, but instead of the feed-forward network, now you have multiple very small feed-forward networks, and you only activate them sparsely using the techniques I showed you before. There are many ways you can do this routing. This is, again, another review. But if you focus on the most common one, the top, what I described to you. So you take every token, you pass it through basically a Gumbel-Softmax. It's not really a Gumbel-Softmax, but it's very close. And it will tell you, okay, 2. And so you will route this token to expert 2, and you can go to the output. And this is a visualization. So you see you have the router, the tokens, the router, and it sends tokens to the different experts. Again, why? Because this is something that is investigated a lot right now, Google, but also OpenAI, probably. One reason is that it's a nice way of quickly multiplying the number of parameters, because you can have as many experts as you want, and they will not worsen your computational costs, because maybe some of them will, let's say, will only activate them depending on the tokens that are routed. The second interesting thing is that they can be parallelized, because once you partition the tokens, I will see that later on, you can execute these experts in parallel if they are on different GPUs. And the reason I like them is that if you're able to make these experts specialize a lot, then ideally you could probably reuse and interpret these components. We'll see that. And we'll also see they are very nice for multimodal and multitask problems. They have some issues. I don't have time to go into the issues, but for example, routing is a little bit difficult because it can collapse. Like GAN collapses, etc. So sometimes you get that the optimization will just use a very small number of experts. And implementation is tricky. You typically need some additional libraries, especially if you want to truly parallelize everything. This is an example of parallelization. So you see you have routers here, you have different experts. These experts are on different devices. And the idea is that you have your pictures here, they're your tokens. The router is partitioning them to different experts. So you need some way of quickly communicating this token through the different devices, but then the expert can be executed in parallel. So if you have, let's say, very big architectures and very well-made, let's say, hardware infrastructure where these GPUs are highly interconnected, it can improve a lot the scaling vision with sparse mixture of experts. But the reason I like them, as I told you, let me just give you one example, maybe it's a little bit easier, is that they are a very, very nice fit for multitask and multimodal problems. So imagine this scenario where, and this is another Google paper from last year, where you have a multimodal input. So you want your neural network to be, imagine a ChatGPT where I can write, but I can also talk, for example, or maybe I can take a picture. So the input here can be a picture, it can be a text, it can be a lot of different things, but I don't want to go into different neural network. I want my neural network to be able to handle everything. And the idea is that if I have a mixture of experts, I can basically design this easily so that different experts specialize on different types of data and they don't interfere. So I will have some parts of the network that are specialized on text, some parts that are specialized on pictures, and some parts that are maybe shared across different modalities. It's rather easy, and this is taken from, again, from this Limoy paper, but you can do that again with some kind of simple regularization, an entropy regularization, where you want that basically given some modality, for example, the selection of expert is very specialized, and then you use all the experts, basically. So this is, you can implement this in a couple of lines of code, and it will do what we're telling here. And interestingly, they can specialize. So then what you can do is that you can take each expert and you look at the tokens that are rooted to that specific expert. And sometimes you can see some interesting patterns. So for example, this is an expert that seems to be specializing on textures. This one seems to be specializing on words, etc., etc. So you see, that's something you can do with a standard neural network, because in a standard neural network, everything goes everywhere. So you don't have this encapsulation. Here you have small blocks, sparse routing. So you are encapsulating possible behaviors, which is really interesting. And what we're trying to do here now in terms of research is exploiting this, for example, for continual learning. So the idea is that you not only do you have multiple modalities, but you may have multiple tasks, multiple problems. And these experts are specializing on different problems, on different tasks. And so you can learn a lot of different things sequentially by pushing them into the appropriate blocks inside the neural networks. This is still a work in progress. We don't have, we're finalizing, let's say, a few ideas. Let me skip this one. Third one is very quick, but I wanted to conclude this overview. So we've seen that you can use discreteness to remove layers, and you can use it to remove blocks, let's say. And in both cases, you get some interesting things, let's say. You can also, turns out you can also use it, and that's the last thing that is missing, to remove inputs. So like before, you have the picture, you have tokens, and you can select interesting tokens, and then you can take the prediction based only on these interesting tokens. And you can do that because it's, again, another discrete selection problem. You can use, again, Gumbel-Softmax. Why is this? It's interesting because the transformer can still work. This is something you cannot easily do, for example, with a convolutional set. It only depends on pairwise comparisons, basically. Why is it interesting? Because it gives you, of course, many people have done that. For example, this is a paper from NVIDIA from last year, but they do basically what I described you. So this is the picture. It's divided into tokens. The tokens are the patches, and you have the transformer blocks. And in the middle of these transformer blocks, you put basically a Gumbel-Softmax to remove some patches. An interesting thing is, if you look at the patches at the end, you see you have some kind of saliency. So it seems like it's focusing only on the interesting parts of the picture. And this is really interesting because I don't know how many of you have toyed a little bit with explainability, but explainability, it's really, really hard, keeping standard explainability, because you need to train a neural network, and then you need to plug something on top of the neural network, like Lime or SHAP, and you need to hope that what you get is good. Here, you don't need to do that, because you are sure that these are the interesting tokens, because those are the tokens that the network has selected and that it has used to make the prediction. So you are 100% sure that those are the important tokens for your this particular prediction, which is really, really nice. And again, now interesting thing is that you're moving this selection not outside, so using SHAP, for example, but inside the neural network. So ideally, we could use it to do some more interesting things. For example, one other idea we are pursuing now, again, another project that we are trying to get some funding for, is what we are calling human in the loop explainability. Actually, we have a PhD that is starting now also on this. And the idea is that assume that you have this architecture, and this time we put some human evaluation in the loop. So the human looks at the tokens that are selected and gives me a feedback. And since this is a part of the neural network, I can use this feedback to regularize the choice that has been made. So for example, if some tokens were selected, but a human tells me that they were a bad choice, I can regularize this token selection procedure to try to avoid this selection. So I can kind of correct its behavior. And this is really interesting because it can give me like a lever to control this thing. But it's particularly interesting for me because a lot of the work we do is together with scientists. So for example, we have a lot of projects on paleography. We have a lot of projects on plants, vegetation, let's say, on medicines, etc. And in all these cases, for example, a doctor, typically either it's at the beginning, so it tells me the label of an image, or it's at the end, so I just look at the results. But in this case, I can use his expertise to drive my training, my optimization, which is something I couldn't do before. Again, we hope, and there are some preliminary ideas. Maybe you remember a talk by Petar Velikovic that was at P-Campus, I think 1 year ago. We invited him and he talked about something kind of similar. So they have this paper published on Nature where they help mathematicians prove some hypotheses by a kind of similar idea. So they generate some artificial data based on an hypothesis, they train a model, and then they use some explainability to see why you are getting certain predictions. And this thing is helping the mathematician refine the hypothesis. Basically, we like to significantly extend this work. And my idea is that this is something that doesn't exist, but there are these immense hubs on the internet where you can find neural networks that are pre-trained on many, many different tasks. And in the future, I think we won't have this hub of neural networks. We will have hubs of components that you can plug and play together to build a combinatorial explosion of new neural network. We already have some initial ideas along these lines, but this will be really, really important. Of course, it will have to, we will need to solve a lot of additional tasks, such as recognizing these modules and also stitching them together. And some of these are combinatorial tasks, so it's a kind of interesting problem that we'll have to solve. So again, thanks for listening. It was a kind of a very, very broad and rapid overview, but I hope that it was enough to interest you a little bit in some of this topic and convince you that I think that in the future, this will be a driving design in neural networks. So most of our neural networks will be more modular, more sparse, and we can immediately start thinking about if we do neural network in this way, what we gain from this. So how can we gain efficiency? How can we gain in interpretability? How can we gain in reuse and of the components? Thank you a lot.
Thank you, Simone. Thank you so much. Super interesting. There is for sure some time for a question. So feel free to unmute yourself. Let's say 5 minutes. As an icebreaker, maybe I can start. It's more a curiosity about sparsity, and I would like to ask you if there is any relation of what you talked about with the lottery ticket hypothesis that somehow was a technique, is a technique to reduce the size and of a neural network. So obviously, technically, it is different from what you explained, but somehow the goal is similar. So
it's a good question, actually. I had one. Wait, I had one slide somewhere that I lost.
Exactly. Exactly exactly that
This
slide.
one,
Yeah, exactly, was the slide where this question came to my mind. So maybe if not,
the difference is that when you talk about sparsity, there are two, let's say, paths. One is that you assume that there is some global sparsity, no? So a lottery ticket, like like in the lottery ticket hypothesis, is a global thing. So you extract this subset of weights from the neural network, which you assume it's fundamental for solving your task, no? And there is you need some algorithms to extract this lottery ticket. So the idea is that all the other weights you can just throw them away, okay? Just completely. You don't even need to store them. And so it will be here in this unstructured sparsity. What I'm interested into it's a dynamic sparsity. So it's the idea that actually here conditional computation. So the idea is that maybe there isn't one lottery ticket, no, but maybe each example has a different choice of these weights. So you need a completely different part of the neural network to solve completely different problems. So you cannot throw away parts of the neural network. Actually, you want the network to be as big as possible, but you want to only take the interesting part every time. So they're kind of, let's say, orthogonal. Now, with the lottery ticket, you try to sparsify it and make it as small as possible. Here, you don't care. As long as at every moment in time, you can only take a small piece of the neural network. I hope it answered a little bit.
Okay, thank you. Super interesting. If there are other questions, feel free to unmute yourself.
I killed them. Okay, I mean, even if just maybe what I can do, if you're interested, I can.
Simone, I actually have a question.
I forget. Okay, in the meanwhile, while you say the question, I can try to solve my issue.
Maybe you can just give a pointer instead of giving a full answer now, since it would probably be, I assume, too long to respond. But where would be a good place to start reading if we wanted to understand the problems with collapse that arise when you try and train with modularity?
Good point. So if you, I sent you the link of the presentation in the chat, and I think a very good pointer. It depends on. I mean, collapse has mostly been studied in mixture of experts, let's say. Because the issue is that if you have collapse, if you're using mixture of experts to train in a parallel way, if you have a collapse, you lose this. And so this review can be a starting point. Again, this one. And then there is another paper which could be interesting for you, which is from last year, that is focused on this. But basically, it's a problem of optimization. So maybe one expert, at the beginning is slightly better than the other. And the easiest thing you can do is throw everything to that expert. No? So you get like stuck in a local optimization, local solution, local mix minimum. But you can solve it by, I don't know, some noise or some regularization, balancing, many different techniques.
Great, thanks.
Okay. If there are no other questions, maybe we can just wait 30 seconds if any of you wants to ask something. Otherwise, thank you again, Simone, and maybe then we can in the future explore together the relation between ticket hypothesis, lottery ticket hypothesis, and what you instead explain today.
Sure.
Thank you again.
I wanted just to say again that if you're interested in this, feel free to write an email or contact me anywhere. I'm happy to answer if I have some material, or even if it's a start of a small collaboration. We are very happy to collaborate.
Yeah. Basically, now I'm super interested in emergent abilities and properties of large language models and sociology of large language models, but also on more, let's say, basic and fundamental principle of deep learning as well. So yes. So thank you again also to everybody that joined us. Next Tech Talk will be next week, I think on Thursday. Same hour. Please check our social media. Maybe Vige or Marcello can post here our Twitter or LinkedIn. Next one will be by a researcher. He's a mathematician, but now he's pushing research in at the interface of let's say genomics and machine learning, and in particular we'll talk about representation theory in transformers. It's coming from Trieste, area di ricerca, and so if you are interested, see you next Thursday, next week. Okay, thank you again. Thank you so much, Simone.
Bye.
Bye to everybody.